Hello, geometry students. Welcome to our 7.6, 7.7 notes. We're going to talk about dilations and scale drawings. So a dilation is a type of transformation. Now, we've talked about transformations before. A transformation is an operation that maps an original figure called a pre-image onto a new figure called the image. So the image you start with is called the pre-image, and the image, what you end up with after the transformation, is called the image. So let's take a look at this quick write. There are two kinds of transformations: congruence transformations, let me underline that, congruence transformations and similarity transformations. So how do you think they are different? We're going to draw a couple of examples of a pre-image and an image in a congruence transformation and a pre-image and an image in a similarity transformation to see if we can compare the two types of transformations. Well, first of all, let's just recall when we studied transformations before, we were studying congruence transformations, and the three we studied were translations, reflections, and rotations. So let's just take an example of one of those. Let's just pick a translation. So for an example of a congruence transformation, I am going to sketch a triangle, and then let's just do a transformation that's a translation to the right. So let's call this triangle ABC, and I'm going to translate that triangle to the right, and when I do, my image ends up being, well, I tried to draw a triangle that looks congruent. Its name would be A prime, B prime, C prime. And so just the matter of taking each point and shifting it to the right, we end up with a triangle that's congruent to the original. So that would happen with a translation or a rotation or a reflection. But now let's take a look at an example of a similarity transformation. And the similarity transformation that we're going to talk about is a dilation. So similarity transformation. Okay, so I'm going to take a small triangle. Let's call it triangle ABC, and then I'm going to dilate that. I'm going to make it bigger. Okay, and we end up with a triangle that's not congruent to the original triangle, but it is similar. They are the same shape and the same size. So notice in a similarity transformation, let me draw an arrow to say that we dilated. Okay. In a similarity transformation, you won't end up necessarily with a congruent shape like you would for a congruence transformation, like a translation or a reflection or a rotation. Okay, so let's talk about the definition of a transformation and kind of nail that down. So a dilation is a transformation that either enlarges or reduces an original figure. And when it does that, it's going to do it proportionally. Okay, remember, if it's a similarity transformation, then the image will be proportional to the original, to the pre-image. Okay, dilations are performed with respect to a fixed point called the center of dilation. Center of dilation. Now, anytime we have a dilation, there's going to be what's called a scale factor of dilation. That determines how much the figure, the pre-image, is either enlarged or reduced. So the scale factor of dilation, we can find that by taking the ratio of the length on the ratio of a length on the image to the corresponding length on a pre-image. Okay, scale factor is often represented by the variable k. So let's take a look at this example where triangle JKL, this green triangle, is a dilation of triangle ABC. Triangle ABC. Okay, the center of dilation is right here. It's at the origin. So our center of dilation is 0, 0. And the scale factor, now remember from the definition of scale factor, it's a ratio of a length on the image, that's the new shape, to the corresponding length on the pre-image. So for example, we could take the ratio of JK to AB. JK and AB would correspond. So remember, every time you write a scale factor, you always want to write the new over the old. Okay, so the image is the new shape, the pre-image is the old shape. So if I take that scale factor, I'm going to take this new segment JK and put it over this old segment AB. So that scale factor we can call JK to AB. Now we could have taken any other two pair of corresponding sides. We could have said KL to BC or JL to AC. Now when we have a dilation, we call it an enlargement anytime we have a scale factor that's greater than 1. So for example, in this dilation right here, let's go ahead and call this blue triangle the smaller triangle. Let's go ahead and label that as the pre-image. And then let's go ahead and label this bigger triangle as the image. Okay, so you can see how if we were to take a ratio of any corresponding sides where we take a new over the old, an image, a side of the image to a side of the pre-image, you can see how RS would be larger than FG, so we would have a scale factor that's bigger than 1. So a dilation is called an enlargement when the scale factor is bigger than 1. It's called a reduction anytime the scale factor is less than 1, when K is less than 1. So for example, let's go ahead and label this larger quadrilateral as the pre-image. And then the smaller one, let's call it the image. So again, if we were to take a ratio of a side of the image to the side of the pre-image, so for example, WZ over AD, you can see how that would be a ratio that's clearly less than 1. So an enlargement when the scale factor is bigger than 1, a dilation when the scale factor is less than 1. So let's take a look at these to determine whether the dilation from figure A to figure B is an enlargement or a reduction. Then find the scale factor. Okay, so we need to remember that we're going from A to B. So that means A is our pre-image. So A will be the pre-image. Think of that as the old shape. Oops, I spelled image wrong. And then B is going to be the image. So think of that as the new. So pre-image is old, image is new. Okay, so let's take a look at this one. We're going from A to B. So if we go from this blue triangle to this green triangle, going from A to B, I think you can tell that that's going to be a reduction. And we can prove that it's a reduction because we can find the scale factor. So the scale factor is the ratio of any new to old ratio. So let's, for example, let's look at this segment that, well, that appears to be 3 units long and put that over this old segment that would be over 6. So our scale factor is 3 to 6, or that would reduce to 1/2, which of course is less than 1, and we can tell that it's a reduction. Okay, how about letter B? Now we're going from A to B. Okay, so I think we can tell that that's an enlargement, and the reason why it's an enlargement, enlargement, okay, and the reason we know that it's an enlargement is because the scale factor, if we take the ratio of an image point to a an image segment to a pre-image segment, we can see that that would be 4 units to 3 units, which is definitely bigger than 1, and it should be because this is an enlargement. Okay, in letter C, we're going from A to B, so that's another enlargement. Okay, so that's an enlargement. Enlargement. Okay, and we know it is because the scale factor, if we take the ratio of a side of B to a side of A, looks like that would be 5 units to 4 units. 5 over 4 is bigger than 1, and it should be because this is an enlargement. And then the last one, if we're going from A to B, that looks like it's a reduction. And we can show that it's a reduction by looking at the scale factor. So I'm going to take a measure of a side of the image and compare it to a measure of the side of the pre-image. So that would be 1 to 3, which is definitely less than 1, as it should be since this is a reduction. So now let's look at some examples where this idea of similarity and proportionality that we've been studying, where they become really practical. So we're going to talk about scale models or scale drawings. So a scale model or a scale drawing is an object or a drawing with lengths that are proportional, okay, to the object that it represents, okay? The scale, and notice I didn't say scale factor, but the scale of a drawing or a model is the ratio of a length on the model or drawing to the actual length of the object being modeled or drawn, okay? So in other words, we're going to take a ratio of a measure on the model to a measure of the original, okay? So again, that's kind of that same new over old idea when we go to find the scale. So for example, let's look at this first one. The scale on the map is 0.4 inches on the map to 40 miles in reality. If the distance from Nashville to Memphis on the map is approximately 1.5 inches, find the actual distance in miles from Nashville to Memphis. So we're going to use this scale. Now the scale is going to compare a measure on the map, 0.4 inches to 40 miles in reality, okay? So now if we want to answer the question, if the distance from Nashville to Memphis on the map is 1.4 inches, find the actual distance from Nashville to Memphis. Let's call that actual distance, let's just give it a variable, let's call it x, okay? So let's write a proportion that compares, now this ratio compares a measure on the map to a measure in real life. Okay, so what would go up here? Would it be the 1.5 or the x? Remember, 1.5 is the measure from Nashville to Memphis on the map, so that's going to go in the numerator, and then x represented the actual distance from Nashville to Memphis, so that's going to go in the denominator. So notice in both ratios, it's a comparison of inches to miles. Remember, we've said there's lots of correct ways to write a proportion, but once you write that first ratio that set the pattern comparing inches to miles, you need to make sure that this ratio compares inches to miles. So we can cross multiply and divide. I'm going to try and save us some time on this video and cross multiply. Just go ahead and tell you the answer. After you cross multiply and divide, it turns out to be 150 miles. Okay, so you can ask yourself if that seems reasonable. If 0.4 inches represents 40 miles in reality, then 1.5 inches seems like it could represent 150 miles. That's a reasonable answer. So let's take a look at this next example. It says the height of the Chrysler Building in New York City is 1,050 feet. Imagine making a miniature replica that is 15 inches high. Okay, so the first thing we're going to answer is, what is the scale of this model? Well, remember, scale is a ratio, okay, and the scale is going to compare units. Okay, so think of it that way. It's going to compare units. So our scale would be, now remember, when we write that scale, we want to write a ratio, and the numerator of that ratio is going to be a measure from what's new, so that would be your model. So I'm going to just put model length. Oops. Let me write that so it's actually readable. Okay, model length. Let's compare model length to the actual length of the building. Okay, so that would be, we're told that the model is going to be measured in inches and the actual building is measured in feet. So that scale is going to be 15 inches. What we want on our model will represent 1,050 feet of the actual Chrysler Building. Now, as we said when we started this unit, when we're dealing with ratios have the most meaning when we reduce them. So I'm going to go ahead and reduce this. 15 would go into 1,050 70 times. So this will reduce to 1 inch over 70 feet. In other words, 1 inch on our model represents 70 feet on the actual building. So then let's answer this next question. How many times larger is the Chrysler building than the model? Remember, your model is only 15 inches tall. So how many times larger is the actual building to the model that maybe you could sit on your mantle? So the difference between letter A and letter B is this time we're being asked to find, another way to ask this would be to say, find the scale factor. Now, factor means multiplication, right? So in other words, how many times bigger is this actual building than your model? So when you think about scale factor should be unitless. In other words, units shouldn't be considered, as they were up here when we talked about the scale. The scale compared inches to feet. It's a comparison of units. Scale factor is unitless. So here's how we'll figure out what the scale factor is. Let's take our scale, which is 1 inch to 70 feet. Now, what I need to do is, if I'm going to come up with a scale factor, these units need to be the same. So I'm going to convert everything into inches. 70 feet. Well, every one of these 70 feet would have 12 inches. So in other words, I'm going to convert 70 feet into inches just by multiplying 70 times 12. And when I do, I get 184. So in other words, 1 inch to 70 feet is the same as 1 inch to 840 inches. So now that these units are the same, we can actually just think about canceling them. So in other words, the scale factor is 1 to 840. In other words, the Chrysler building is 840 times the size of our model that's only 15 inches tall. So to answer the question, how many times larger is the Chrysler building than our model that we built? We can say it is 840 times larger. Okay? All right, and then one more example. The last example says, the St. Louis Gateway Arch, the tallest national monument in the U.S., in case you didn't know that, is 630 feet tall. Suppose you want to build a model that is no more than 11 inches tall. So no more than. It doesn't necessarily need to be exactly 11 inches, but just no more than. So choose an approximate and appropriate scale to use to determine the length of the model. The height of the model. Okay, so let's start by choosing an approximate scale. So if we look at our scale, remember scale compares units. So 11 inches on our model, we're going to compare that to 630 feet of the actual building, okay? Now, what I'm going to do, since we're approximating, let's go ahead and pick some numbers. Let's just round these numbers a little bit. I'm going to go ahead and round 11 down to 10 and 630 down to 600. So this would be approximately equal to 10 inches to 600 feet, or we could even reduce that and call it 1 inch to 60 feet. So that's the scale I'm going to use, 1 inch to 60 feet. And again, it's an approximate scale because we rounded here. So there's an approximate scale I'm going to use to determine the height of my model. So now I can write a proportion. I can say, okay, 1 inch to 60 feet. Let's compare that to the ratio of how many inches I want my model to be to the actual height in feet of the St. Louis Gateway Arch, which would be 630 feet. Okay, so notice when I wrote this proportion, again, I compared inches to feet in the first ratio, so I need to make sure that my second ratio is consistent and we compare inches to feet. So now if we cross multiply, we're going to get that 630 is equal to 60 times x. We'll divide both sides by 60, and x is approximately equal to 10.5. And again, this is very, very approximate. Now, that x, remember x was a number of inches, so that would be 10.5 inches. Okay, so if we use a scale of approximately 1 inch to 60 feet, then and we want our model to be proportional to the original. We'll take 1 inch to 60 feet and compare that to x inches to 630 feet, cross multiply and solve, and our model would be about 10.5 inches. Okay, so you will get some more practice on some problems like these in class, and I will see you then.